Hi, everyone. My name is Drew Prinster, and today I'm very happy to share with you our work, Conformal Validity Guarantees Exist for Any Data Distribution and How to Find Them. So this is a paper at ICML 2024, and it's joint work with Samuel Stanton, Angie Liu, and Suchi Saria. Okay, so first for a little roadmap on the talk today, I'll give you, for those who are less familiar with conformal prediction, I'll give a quick introduction on what that is in the context of AI uncertainty quantification. And then some key background on related work. I'll sketch the key ideas and the theory and methods in this paper, and then quick highlighting of experiments, and then some quick discussion and takeaways. Okay, so conformal prediction, represented here in this diagram, is an approach to AI uncertainty estimation, which specifically computes this predictive confidence interval or set. And one really nice thing about conformal prediction is that for under standard assumptions, it has this coverage validity guarantee. And so what is this guarantee saying? It's saying that for some input test point, X test, the true label Y test that we're trying to predict is actually contained in this confidence interval or set with some probability at least 1 minus alpha, where 1 alpha is specified by the user. So this could be, say, like 90%, or if you want a 95% confidence interval, you could specify it that way. And so, yeah, roughly coverage is saying that you actually have a reliable interval here. But traditionally, conformal prediction has relied on this key assumption called exchangeability. And so one example of exchangeability is IID, or standard independent and identically distributed assumption. And so roughly this is saying that exchangeability is saying that there's no distribution shift between the test distribution and the distribution you're using for calibration, for calibrating these intervals, which is often, this is usually the same as the training distribution. And so this excludes actually many important use cases in the real world where there are changes over time or across data batches. So this could be like data collected by AI agents, where actions at one time step might introduce feedback loops that accumulate and cause further shifts in the future. Or also dynamic time series, where there's some shifts associated with time. Or structured data where the ordering of observations is really important. And so the main question that we look at in our paper is, theoretically, can standard conformal prediction is this with this exchangeability assumption, can it theoretically extend to actually any data distribution? And we specifically look at these applications for AI agents, which I've mentioned as having these feedback loop shifts. So I think an important and increasingly common use case. And so as a quick spoiler or preview, the answer is yes. Theoretically, we can extend conformal prediction to any potentially non-exchangeable data distribution. However, there's important caveats there regarding practical implementation. So there's with the benefit of generality, there's some strong practical bottlenecks that will come up, which we'll go into. But for practical applications, we outline how to find these conformal guarantees for any specific distribution. And we focus on this case of AI agents that I've mentioned, where we have these iterative feedback loop shifts. Okay, this is highlighting what I said here, so that, or just now. So yes, in theory, we can extend to any potentially non-exchangeable distribution. And I really want to highlight that this builds a lot on analysis from Tibshirani et al. 2019, which I'll go into. And so, yes, for these practical applications, how to find these guarantees, these AI agent feedback loop shifts. And lastly, we look at some, I think, cool extensions that are, I think, closer to real world settings where you might want adaptive AI exploration that like initially exploring slowly to stay safe or satisfy some other criteria, and then explore more aggressively once you have more experience. And doing this, in our case, by maintaining sharp and informative intervals. Okay, so key backgrounds for related work, we focus on weighted conformal prediction. Under related work here is on weighted conformal prediction for covariate shifts. There's other works outside of this that also look at conformal prediction under distribution shift, which I won't go into here, but we try to reference in our paper, so can look there for other references. So for historical context, conformal prediction was initially developed by Volk et al. This is the reference to their book on conformal prediction, and traditionally relied on this exchangeability assumption where there's no, roughly no shift between calibration data and the test data. More recently, Tibshirani et al. Extended conformal prediction to this, from exchangeability to this relaxed, what they called weighted exchangeability criteria. And so roughly you can think about this as shifts that are independent of each other. And so independent statistically, so not yet looking at statistical dependencies between shifts, such as the feedback loops that I mentioned. And so one important and common example is standard covariate shift. So this is where the input distribution of the x's might change from training data relative to test data. But we assume that the y given x distribution, the relationship between the output and the input, remains the same. And so more recently, Fan Zhang et al. Looked at this further extension of conformal prediction to what they called potentially pseudo-exchangeable data. And pseudo-exchangeability has notation that is more explicit, allows for explicitly accounting for these limited dependent data shifts. So allowing for this arrow here, potential dependency of one test batch on an initially observed training batch of data. And they specifically look at this condition they call feedback covariate shift. And so the difference between feedback and standard covariate shift is this arrow here, which is the dependency of the test data on the training data. And so for our paper, we look even more generally at how conformal prediction could, in theory, extend to actually any data distribution. So theoretically, this could be like any distribution shift. And we specifically look at what we're calling this multi-step feedback covariate shift setting, or I'll just say MFCS, and this characterizes these important use cases for AI agents that we'll go into, where we have these feedback shifts. And so I'll note that this is MFCS is similar to a setting in Nair and Jansen 2023, and I encourage you to look at their work too. And so all of these are still, I guess, also original. All of these are still assuming y given x is invariant. Okay, so now, looking at the, I'll sketch the key ideas and the theory and methods in our paper. And specifically, I'll start with some key work ideas from Tibshirani et al. That we build heavily on, the key insight for our paper. And then looking at the main result, or the title of our paper, that there does exist some conformal validity guarantee for any distribution, and then looking at how to find those guarantees for specific distributions. All right, so the setup from Tibshirani et al., which is important for our paper, is initially starting by collecting just a bag of data points. So here, this Z Zi for each I is going to be used to represent a covariate label pair. So X being the input covariates, and Y being the label we're trying to predict. And so yeah, just I'm using Z to note those before. The condition on this a set equality event between these capital ones are the random variables, and these lowercase are the observations. And so basically just we can think about this as literally for our stream of data where the first n or we assume are calibration data, and let's say just one test point for now. You can think about this as literally just like collecting all of your data into a bag, where the bag is here emphasizing that we're sort of forgetting or losing track of which data were calibration and which data were your test point. And so this sort of epistemic like abstention, I guess, or like this forgetting is an important source of uncertainty for conformal predictions, uncertainty quantification. So yeah, just stating this here, we know that each random variable data point takes a value in this set of observations, but we don't know which one. And same for what these score values, which I'll now go into. So conformal prediction builds or uses what they call non-conformity scores. So this is in the initial formulation of conformal prediction, where non-conformity, where conformal gets its name from, it's roughly referring to so how different is this data point from other examples that we've seen. So this is this score function, and it can be fit with some machine learning model. And this value VI is representing this like strangeness or non-conformity. So a common example is residual scores, where so this so you're probably familiar, just absolute difference between the Y label and some fitted prediction of that label. And so then you have these bag of data, and you then get this oops, that's supposed to be a bag of scores, and then you use that bag of scores to compute this roughly 1 minus alpha quantile, or it's like a percentile. So you basically take like roughly the 90th percentile, if you or 95% percentile. Again, this is a user specified level. And that quantile is key for constructing the conformal prediction set. So this is just standard conformal prediction still. But the key insight for this Tibshani et al. Proof is looking at a weighted generalization of conformal prediction, which allows them to extend conformal to what their weighted exchangeability criteria. And so this might look intimidating. This statement might look intimidating at first, but I'm going to walk through it more closely in the next slide. But the important takeaway here is, firstly, that these weights that they're looking at correspond to like given the bag of data, so conditioning on the bag of data, what is the probability that the random variable capital Vn plus 1 corresponding to the test points score was actually this specific score from the bag of scores. And so again, this is going back to, this is why I was emphasizing before that you're sort of forgetting the identity of each of the data points, because then that's what makes this make sense. You can think about like, what is the true probability that the true test point score was actually this specific one after like putting them all in a bag and drawing them out. And so this is like breaking this bag construction is like broken the connection between the random variable and observation indices. And so then they this alternate formulation of standard conformal prediction and this extension to weighted exchangeability is what all from Tibshani et al. And so now moving on to the key insight in our paper, um, the main observation that's important in our paper is, or for our paper is that these exchangeability conditions or steps can actually be thought of as practical rather than theoretically necessary steps in the proof. And so this permits a even more general formulation of conformal prediction, which I think has some helpful conceptual benefits, which we'll look into. Okay, so diving into what I think can help for some intuition for this general view of conformal, I'll just try and sketch like what this step that I skipped earlier, this yellow asterisk here is is saying, like, how do we get this connection? So for F denoting a joint probability density function, or it's going to be a probability mass function, how do we make this connection? So first, this is firstly just equating what are initially probabilities on observation of the score of the conformal scores to instead event on the data. And so there's some details in the paper on why this holds, but it's because this score function S hat is inducing a bijection between the data point values and the score values, so that we can equate these, or specifically it's an injective function is what you need. And then just using standard tools from probability theory, if we just think about like what this statement now is saying, it's conditioning on this bag of data, it's conditional probability. So writing this out, this is just the joint distribution or joint density of these two events here, divided by the marginal density of observing this bag of data. And then the next step, which I think to me this statement here initially looked a bit intimidating, but if you think about it, this is just the law of total probability over, so I guess I haven't said what sigma is yet. Sigma is a permutation. So just like a shuffling or reordering of the data indices. And so this is a law of total probability in both the denominator and the numerator. So looking at the denominator case, the probability of observing, or density of observing a specific bag of data points can be thought of as the sum over the density for each different ordering that we could have observed those data in. And then the numerator is just specific set of permutations, the set of permutations that map the test point index n+1 to the index I. And so our paper, rather than premising a form of conformal prediction on a definition of exchangeability, we then proceed directly from this step to derive this general form of conformal prediction. And so, once we view that these exchangeability conditions not as theoretical necessary conditions, but just as these practical steps, I think it can be helpful for understanding that like that there are these guarantees for any F. This statement holds for constructing this empirical weighted distribution of scores, and can have this general form of conformal from it. And so I want to highlight here, and I'll go more into some benefits and drawbacks, but so the only role of exchangeability assumptions is to generally simplify these weights into a tractable form. So one challenge here, what do I mean by tractability? One challenge is complexity, because this is a sum over permutations. So this computational complexity will be factorial, which is not often tractable in most cases. And another one is knowledge about this F. this joint distribution. And this is also a challenge with other like weighted exchangeability or pseudo exchangeability. You need to know basically like what are the dynamic or changing components of the distribution to generalize it. And so no worries if that was a bit abstract there. I'll try and go into the example with the multi-step feedback rate shift case. But quickly, the main result is the main title for our paper. So there is actually this general form of conformal prediction for any data distribution. And I want to mention that this insight and form of conformal prediction is implicit in Tibshrani et al. 2019, but the authors did not explicitly state or prove that result, prove this result in that paper. And so we think that this insight has been underappreciated in the literature, which we think, so yeah, hopefully our contribution can help correct that oversight and lead to more practical utility. And so what this is saying real quick, so these are the weights that we were looking at earlier, looking at the corresponding to the height of how much weight we put on a given score value in the general distribution. And each point mass is like, so the delta here is a point mass. I'm just denoting the location here. And this infinity is an important, corresponds to an important conservative adjustment in conformal prediction. We're defer to the paper for those details. And so this is just the general validity guarantee for, this holds for any f, any joint density function f. Okay, and so now for like actually specific practical applications, we look at the second component of like, how do we actually find these conformal guarantees for any specific distribution f. So focusing, and we'll give this for the specific MFCS case. So firstly, can just like list any assumptions, if any, on the data distribution. And this can be just like trying to clearly describe what the assumptions you can make in a given application setting, or that you just have to make due to practical considerations. And so for our case, we're just going to be looking at some AI agents cases. This is allowing the input distribution to change depending on past observations, but still requiring the no concept shift, no change in the relationship between output and input. So then the second step is to use our assumptions from step one, if any, and standard probability rules to factorize the joint distribution into some dynamic factors and invariant factors with respect to permutations. And so for multi-step feedback covariance shift, here just using T to denote potentially more test points. This allows for these dependent factors, which roughly correspond to X changing based on past observations. And these invariant factors, which corresponds to this assumed invariance in Y given X there. And defer to our paper for how to drive this. And then the last step is to compute or estimate these weights. And so can plug this factorized form of the joint data distribution into the general conformal weights that were the height of each point in the score distribution we looked at. And this invariance here, this assumed invariance is what's going to help us with the tractability of this intimidating statement. So specifically, this Y given X is going to cancel out after being plugged into the ratio here. And that's because it's invariant to permutations, or I say time here because we're allowing our time steps to represent our data indices to represent time. And so, um, but generally it's permutation invariance that you care about. And so, yeah, this is going to cancel out in the ratio because it's both in the numerator and the denominator. And so it leaves just this dynamic factor corresponding to how x is changing over time. And so that helps address the bottleneck of knowledge of the distribution in our multi-step agents case, because in each step, this conditional probability of x given the past is going to be controlled by our AI model. And so it cancels out the part that we don't have knowledge of. And further, for addressing the complexity bottleneck, we propose approximating this statement by limiting this product to just a finite or a small estimation depth. So D here is our estimation depth that we'll use for practical experiments. And so hopefully also readers of our paper can have other creative uses for this procedure. We welcome your building on this work. But now moving on to our specific experiments, we look at instances of machine learning agents such as black box optimization and active learning, and some extensions of active learning for this adaptive exploration. And so specifically, our black box optimization will be a multi-round synthetic protein design. And so, as I mentioned before, this is representing our query strategy, our query function for the AI or ML agent for some utility function that you're trying to optimize for. And these experiments demonstrate, well, relative to the baselines of exchangeable standard conformal prediction, which can lose coverage, and prior baseline on conformal just for one step covariate shifts without accounting for this multi-step accumulated feedback shift. Whereas these baselines can lose coverage, our proposed methods here maintain coverage over different numbers of different steps in the protein design process. And this is all optimizing for fitness here, where fitness is the utility function. So fitness could be like medical efficacy or therapeutic potential, or specifically for us, we're looking at fluorescence. And so our methods specifically maintain coverage by increasing the width of the intervals at later time steps relative to these baselines, or specifically related to the green baseline. And the split conformal methods accommodate complex models like neural networks and other no assumptions on the model itself. So yeah, validating our coverage there. And so next, moving on to the active learning experiments. So first looking at, this is the unbounded query function, the same that we have there, except now the utility that we're optimizing for is the posterior variance of, so trying to select points that are very uncertain that the AI model thinks is uncertain at each time step in order to minimize mean squared error over time. And our proposed multi-step method allows for maintaining coverage above the target level, even at later steps in the time horizon, where baselines lose coverage. However, this is initially with overly large non-informative intervals. And so we look at, can we actually change or modify the query strategy of the AI ML agent to maintain sharper and more informative interval widths? And so this proposed, what we do is basically just bound the magnitude of so we don't put too much probability density on selecting certain points. This enforces much more informative and sharper intervals that can be more useful in practice rather than a non-informative interval is basically just saying, I don't know. And so if we chart the relative magnitude of this bound we're putting on the exploration strategy, we can see it increasing with time. And so this is, I think, kind of cool, basically showing that the bounded agent allows, it is initially exploring more slowly before it's seen enough data to then be more aggressive. And it seems like in these experiments that the decrease in mean squared error is comparable to the unbounded query function, just with greater variability in in that drop. Okay, so now just for some quick discussion and takeaways. To recap, this paper looked at whether conformal prediction can theoretically extend to any potentially non-exchangeable data distribution. And we proved that there are conformal guarantees for any specific distribution. And specifically, we look at provide this procedure for how to find these guarantees for a given application of interest. And we thoroughly develop the case for these types of AI agents with feedback loop data shifts characterized by a multi-step feedback covariate shift. And we look at these extensions for adaptive exploration, which I think are pretty cool. But there's many promising and interesting future directions that I think would be really interesting to explore further. So one of these is just further addressing these practical bottlenecks of the complexity and epistemic challenge of computing those general conformal prediction weights that we looked at. Also specifically related to agents, there's connections with safe decision-making, both autonomously and with human in the loop. Also other loss functions related to conformal risk control, where coverage you can think of as one instance of a loss function. And also conditional calibration. So as a caveat, all of the coverage guarantees we're looking at in this work are marginal, meaning on average over the draw of the calibration data and the test point. Ideally, you'd want some uncertainty that's more individualized. So calibrating for that goal could be important, and probably others that I haven't thought of. And so, yeah, I think I just also want to say that I hope that our contributions can help cultivate a sense of possibility in conformal prediction and invite others to make use of rather than considering these exchangeability conditions as theoretical boundaries, as it seems like they've been thought of, shifting in perspective to instead just try to clearly specify these, use these conditions to clearly specify practical assumptions. So the whatever assumptions on the distribution that are permitted by the application you're caring about, or that are just adopted for practical tractability. So with that, here are the references to many papers that we build on. And I've learned a lot from these authors, so give those a read too. And there's more references in our paper, of course, too. And also thank you to our sponsors. And here's the QR to our paper if you'd like to read more. Also, feel free to reach out. My email is drew@cs.jhu.edu if you'd like to get in contact. Yeah, thank you for your attention and interest. Bye.